All right, 4.8 is inverse trig functions. First, it starts talking about the inverse properties. It says if a function is one-to-one, which means it passes the horizontal line test, then its inverse relation is also a function. For sine, cosine, and tangent, we'll have to restrict the domains for each function to discover these properties. And so remember there, to be one-to-one just means it passes that horizontal line test. So we did this before, like when we were looking at, let's say, a linear function here, okay? And so we could take any horizontal line and we could cross across it, and it's only going to touch it one time. That means that it's one-to-one, it passes the horizontal line test, which means its inverse is a function. We also looked at, like when we looked at a quadratic. And so we did the same thing, but we said, oh, its inverse, it does not pass the horizontal line test, it is not one-to-one, and therefore its inverse is not going to be a function. But we said if we took, like at its vertex here, and we restrict the domain, so we say, oh, let's only look at it from where x is greater than or equal to 0, then, this piece of it is one-to-one, and therefore that piece would have had an inverse that was a function. Alright, so then here it talks about some of the properties and some of the domains for it, but we're going to talk more about that later. So I'm going to, skip over that for now. And so let's look down here. It says, remember that a function will have an inverse if it is one-to-one. And so it's meaning it's going to have an inverse that's a function. Whoops, not the pen. So 1, 2, 1. Functions are one-to-one if they have one x value for every y value, meaning no x's are repeated, no y's are repeated. A function f of x with an inverse, which is written as f, looks like it's raised to the negative 1 of x, but it's just the inverse of f of x, has the following characteristics. If we take their compositions, so if we take the inverse of f and we plug in f of x, it's going to equal x every time. Alright, so it's going to equal x for every x in the domain of f. And then if we take the inverse of f of x and we plug it into f of x, it's also going to equal x for every x in the domain of the inverse. And so we did that before, for example, when we said like f of x was equal to x squared, but we could only look for where x is greater than or equal to 0, so that its inverse is a function. And we said like g of x is equal to the square root of x. So when we took their composition, f composed of g of x, which meant f is my skeleton, and g of x is what we were plugging in, we ended up with x. And then remember we took g of f of x, so now g is on the outside, so it's my skeleton, and we plugged in f of x, so we plugged in the x squared, and it also equaled x. Therefore, we were able to say that f and g are inverses of each other, because when we took their compositions, they both equaled x. Now, remember the big thing about inverses is your x and y values are going to switch. And so if the x and y values switch, that means the domain and the range will also switch. So the domain of f is equal to the range of the inverse of f, and the range of f is equal to the domain of the inverse of f. The graph of f and the inverse of f are symmetric with respect to the line y equals x. And so in the above example that I just did, if I was going to graph f of x, which is x squared, but we had to restrict it to say that it was greater than or equal to 0, so we're only looking at that piece of the parabola. And then g of x, which was the square root of x, so it looks like this. There is this line that comes through here in which they are symmetric about. That is the line y equals x. Remember, symmetric means that we could fold it in half on it, and the two graphs would lie on top of each other. And then number 4 says if a function y equals f of x has an inverse in the equation x equals f of y. The equation of the inverse is x equals f of y. The solution to this equation then is y equals the inverse of f of x. The big thing they're trying to show right there is just remember, x and y switch every time with inverses. Alright, so let's look at the inverse sine function. says first plot y equals sine of x in the interval from negative 2 pi to 2 pi. Well, let's just graph it in the interval that they give us here on our graph. And so remember the sine of x has a parent table of 0, pi over 2 for my x's, pi, 3 pi over 2, and then 2 pi. And my y, sine starts in the middle and goes up, and I left that space on purpose. Alright, and so we graph that. So I'm just going to let every line be, so we're going up to 1, down to negative 1, and each one of these is going to be a pi over 2. And I'm going to extend it all the way through my graph here. It then asks, is this function 1 to 1? Well, let's check the horizontal line test. Does it touch the graph more than once? Yes, it does. Therefore, no, it is not 1 to 1. So that means that we can restrict the domain so that the graph will pass the horizontal line test. Here's a little help. It says find the range of y equals sine of x. So we can see that it goes down to negative 1 and it goes up to positive 1. So the range was negative 1 to 1. Now I want to know what domain value or what x value will give us the range of negative 1. I want the one that is closest to 0. And so we're actually, for that, we're going to back up one block here. This one is closer than this one, so we're going to use the one on the left there. And since it's over one block, that's over left left pi over 2. So we're going to say it's at negative pi over 2. All right. What domain value will give you a range value of 1? Again, closest to the 0. So we're looking up here, which is at positive pi over 2. So we're going to use the last two answers to restrict the domain of y equals sine of x. This domain will become the range of our inverse sine function. So it's saying we're just going to look from here to here. Because if you look, we take on every value, every y value the sine has as we go from one to the other. So what that's saying then is that we are going to, okay, sorry, somebody walked in. All right, so what it's saying there is that we're going to take, and we're going to use negative pi over 2 to positive pi over 2 is what we're going to restrict our domain to. So I'm going to go back over here to my table, my sine table, and so I'm going to back up one. And so we know it's negative pi over 2, and its y value is negative 1. So it's saying we're going to restrict our domain to those values. So if I'm going to restrict the domain to those values, what is going to be the domain and range of my inverse? Now remember, with the inverse, we always switch the x and y's. So doing that, my x's would become negative 1, 0, 1, and my y's are negative pi over 2, 0, and pi over 2. And so that's going to be the table that we're going to use for our inverse sine. Alright, so move it up here so I can graph it. So I'm going to rewrite my table here because I need to see it to graph it so I don't make any mistakes. Alright, so when we go to graph this, we need to figure out our scale. And so what I'm going to do is I'm going to let every line going left and right be every two lines, be a whole number. And I'm going to go ahead and let 2 lines up be pi over 2 and 2 lines down be negative pi over 2. Now when we go to graph this, I have the point negative 1, negative pi over 2, 0, 0, and 1, positive pi over 2. Now it looks like it's a linear line, looks like straight, but remember this is a piece of the sine curve just turned on its side. So it's still going to have that little wave going on in it, okay? Because if we kept going with it, it would continue like this. But we can see that wouldn't pass the vertical line test, so that wouldn't be a function, which is why we had to restrict it. Alright, so in summary, it says for the if f of x is equal to the inverse sine of x, where x's are between -1 and 1 inclusive, and our y's are going to be between -π/2 and +π/2 inclusive. Alright, so let's use that information to help us here. So on the example here, it says remember that y equals the inverse sine of x means that x equals sine of y, because you can switch your x and y's. So our x's for the inverse are going to be between -1 and 1. Our y's are going to be in between -π/2 and π/2. And we're going to use the information to find the exact values of the following problems. So exact means don't use your calculator. Alright, so A says the inverse sine of 1. So remember, when we're doing an inverse, that means it's equal to our angle. So I'm just going to put theta there, which that means if I take the inverse of the inverse, it takes me back to the original. So I'm just going to go back and switch my x and y, my input and my output. And in this case, it would be my theta and my 1. Now remember, we said a few things, that we're looking from -π/2 to π/2 for our answer, because that's the range of the inverse, which means it's in either quadrant 1 or quadrant 4 to be between those two numbers, because -π/2 is down here, +π/2 is over here, and 0 is a point that is in between them two. So we're looking at quadrants 1 and 4. So when you're looking at your unit circle, don't worry about 2 and 3 when you're doing inverse sine. Now also remember that sine is y over r. So this 1, we could say is over 1, but it's y over r. So on my unit circle, r is 1. Tell me where the y value is going to be 1 as well. Alright, so remember, you're only looking though between -π/2 and +π/2. So if you look at the very top of your unit circle, you'll notice that it has the ordered pair up here of 0, 1. That's where our y is 1. That's where sine is going to be 1. And so therefore our answer, for an answer in radians, is going to be at π/2. Now let's go ahead and let's look at C. So C says we're looking for the inverse sine of the square root of 2 over 2. So this means we're looking for the angle. And so we want to know the sine of what angle would give us the square root of 2 over 2. Well, remember on my unit circle, r is always equal to 1. So if you say this sine is y over r, but r is 1, then you know your sine is just going to be that y value, okay? So we're doing inverse sine, which means we're looking in quadrants 1 and 4. We're looking for where y, then it's going to equal the square root of 2 over 2. So look at your angles in quadrants 1 and 4 and find where the y value is the square root of 2 over 2. You'll find that in quadrant 1 at π/4. Now let's look at B. B says we're looking for the inverse sine of -1/2. Well, then that means we're looking for the angle, and so we're really asking sine of what angle would give us a -1/2. Well, just like before, we said we're going to be in quadrants 1 and 4. We're looking for where sine, which is our y value, is -1/2. So look at your ordered pairs, and you'll see it, and it should be at, I believe it's 11 pi over 6. There's only one problem. Remember, we said it has to be between -π/2 and +π/2, which means if I did it as a decimal, this would be -0.5 pi and +0.5 pi. Well, if I look at 11 pi over 6, this is like 1 point something. Okay, it's almost 2. 11 over 6 is almost 2. That number's not in between -0.5 and +0.5. So therefore, what that's telling us, and we kind of did this before, is we're at the right location, but we're given the wrong angle name. So we're right here, which is correct, where we're supposed to be, but I need a coterminal angle for 11 pi over 6 that's going to fit within my domain. Since 11 over 6 is almost 2, it's too big. So what I'm going to do is I'm going to subtract a full circle, and that gives me theta equals negative pi over 6. And pi over 6, negative 1/6, is between negative 0.5 and 0.5 pi. So therefore, negative pi over 6 is the answer we're going to use. You've got to be careful there, guys, because you could be at the right location and still give me the wrong angle measurement, because it has to fit, the angle you give me has to fit within that domain. Or, excuse me, I guess I should say the range, because we're dealing with the inverse sine. And D, they said, we'll be nice. For one thing, 1/3 is not a y value on my unit circle. So this one, without using our calculator, we couldn't do it. So we're going to put this in our calculator. Make sure you're in the correct mode. We're giving our answers unless they're in word problems. We're going to give our answers in radian modes. Make sure your calculator's in radians. And then type in the inverse sine, which is your second sine and 1/3, and hit enter. And it should tell you approximately 0.34. All right, so that's inverse sine. Inverse cosine is very similar. So we're going to do the same thing. We're going to plot y equals cosine of x on the interval that they give us there. It may not be negative 2 pi to 2 pi. So remember, cosine of x had a parent table where the x's were 0, pi over 2, pi, 3 pi over 2, and 2 pi. Cosine started at the top, so it was 1, 0, negative 1, 0, 1. And so I'm going to do the same thing here. I'm going to let this be negative 1, this be positive 1. I'm going to let every line be a pi over 2. Continue your pattern all the way across the available space. Alright, then again, it asks, is the function 1-to-1? Does it pass the horizontal line test? It does not, so no, it is not 1-to-1. So therefore, we're going to restrict the domain. So the first thing we're going to do is find the range of cosine. And again, we can see it goes down to negative 1 and up to positive 1. It asks us what domain value will give you the range of negative 1. Well, I want the one closest to 0. Well, it really doesn't matter which one I choose, because this one's negative 1, this one's negative 1, and they're the same distance. But we don't like negative numbers as much, so let's go with the positive. So we're going to use pi. Alright, give us the range value closest to 0. That's going to give me the x value closest to 0. That's going to give me the range value of negative 1, or positive 1, excuse me. And so that's up here. So that was when x is 0. And so this is going to tell us which x values we're going to look at to be able to find our inverse cosine table. So we're going to look from where x is 0 to where x is pi. So there's where we're going to restrict our domain. And so for cosine, the inverse cosine of x, we're going to switch those x and y's. So my new x's are 0. I'm sorry, my new y's are 0, pi over 2, and pi. My new x's are 1, 0, and negative 1. Alright, so I'm going to move my graph up here so that I can graph it. I am going to rewrite them, because this is the one I will definitely mess up on. So the inverse cosine of x so I'm going to set my graph kind of like I did before. So let my x's be by 1, every 2 lines is a 1. And I'm going to let every 2 lines be a pi over 2 going on my y's. Alright, so when I go to graph this, I've got 1, 0, 0, pi over 2, and negative 1 is up at pi. So again, remember this is a piece of the curve. So try to make it curvy. And so there is our graph. Again, remember if we kept going, whether we keep going above or below, then it wouldn't pass the vertical line test, therefore it wouldn't be a function, which is why we had to restrict using the horizontal line test for the original. Alright, so in summary, we can see here that our x's for the inverse cosine are going from negative 1 to 1, including them. And then our y's are inclusive from 0 to pi over 2. I'm sorry, to pi. Alright, so from 0 to pi. Alright, so let's use this. So same directions as before, just remember the inverse cosine is negative 1 to 1, and it's from 0 to pi. Also remember that inverse y equals inverse cosine of x means that x is equal to cosine of y. Alright, so A wants us to find the inverse cosine of 0. When you're doing an inverse, you're always looking for an angle, so let's set it equal to theta, which is take the inverse of the inverse to take us back to the original. And so we got cosine of theta is equal to 0. Now, we did say that cosine's from 0 to pi, inverse cosine, so that means that we're in quadrants 1 or 2. Remember that cosine is also x over r on our unit circle, though r is 1, so therefore we're just looking at the x coordinate, okay? So where cosine is 0, that means I'm looking for where my x is 0. So where in quadrants 1 and 2, from 0 to pi, is my x value going to be 0? Well, x is 0 on the y-axis, so it's up there at the top, when our angle is equal to pi over 2. Alright, let's jump down to C again. So C wants to know the inverse cosine. What is the inverse cosine of square root of 2 over 2? Again, it's going to be equal to theta because we're looking for an angle, which I want to know cosine of what angle would give me the square root of 2 over 2. Now remember, you're looking in quadrants 1 and 2. Cosine is your x value, so I want to know where is the x going to be the square root of 2 over 2. And so that is happening at pi over 4. Now, B says the inverse cosine is equal to, inverse cosine of negative 1/2. So it's inverse, so we're looking for the angle, which means cosine of what angle would give us a negative 1/2. Well, cosine is our x. Remember, we're looking inverse cosine, so we're only looking in quadrants 1 and 2, which for x to be negative means I'm really looking in quadrant 2, and I'm looking for where the x is a 1/2. And so that should be at 2 pi over 3. And then D says estimate the inverse cosine of 1/3. Again, just like the other one we just did, we don't have 1/3 as an x value on our unit circle. So we're going to plug this in our calculator, so make sure you're in radian mode. And then second cosine of 1/3, and it tells us it's 1.231. Alright, just double check myself. Alright guys, so that's inverse cosine. And let's go on to inverse tangent, and then we'll start a second video. Alright, so inverse tangent. Same thing. It says plot y equals tangent of x in the interval from negative pi to positive pi. And so I think we might be able to fit that one on here. So remember, tangent of x starts at negative pi over 2, and it goes to positive pi over 2. for your x's. It's undefined, and then it drops down to the bottom and comes back up until it's undefined again for the y's. Alright, so if I do like I did before, we're going to let every line be a pi. We could actually go, no, these are about pi over 4, so we're going to let every line be a pi over 4. Alright, so negative pi over 2. Then it goes negative pi over 4, negative 1, 0, 0, pi over 4, 1, pi over 2. Repeat your pattern. Alright, so there's our graph. And so we can see that, is this function 1 to 1? No. Right here, when I just do that horizontal line, it does not pass the horizontal line test. So no, it's not. So we're going to restrict the domain to only one period, so that the graph will pass the horizontal line test. If you look at this, if I take off this piece I have here, and I take off this piece that I have here, and I just look at one period, that does pass the horizontal line test. So one period of it does make it 1 to 1. So that's what we're just going to restrict it to. So we're only going to use these values right here. Alright, so then when we go to do our inverse tangent table, we're just going to switch those x and y's. So my new x's are undefined, negative 1, 0, 1, and undefined. And our y's are now negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. Now remember, with the tangent we had vertical asymptotes, and so with the inverse tangent we're actually going to have those horizontal asymptotes. Alright, so sorry about that up there. I'm going to move this up so I can graph it. Alright, I'm going to rewrite it so I don't make a mistake. Alright, and so let's label. See, I'm going to let my x's be every 2 lines is a 1 again. And let my y's be every line is a pi over 4. Now I know what my negative and positive pi over 2, so it's undefined, so it's going to be my horizontal asymptotes. And then I can just plot my other points. Negative 1 is negative pi over 4, 0, 0, and 1 is pi over 4. We're going to connect those, and they're going to be shaped by our asymptotes here. So it's going to be a little curved line, and it's going to keep going. And so we can see here, looking at that graph, that our x's keep going from the left to the right, and so they really should just be greater than because of the infinities. And we can see that our y's go from negative pi over 2 up to pi over 2, but again it should just be, I said greater than a minute ago, sorry, it should be less than symbols because they're not equal to because of the asymptotes as well. Alright, so now let's try some problems here. So example 3 says, remember that y equals the inverse tangent of x means that x is equal to tangent of y. We're looking for our x's to be between negative infinity and infinity, and our y's to be between negative pi over 2 and pi over 2. So we're going to use this information to find the exact values of the following problems. Now these you have to think a little bit more than the other ones because tangent, remember, is not x and is not y, but it is y over x. So a few things is we know we're looking for y over x. We also know that because it's from our range is from negative pi over 2 to pi over 2, again, negative pi over 2 to pi over 2, sorry about that, again means that we're looking at quadrants 1 and 4. All right, so when I have the inverse tangent of 1, the inverse means we're looking for an angle. So remember, that means I want to know tangent of what angle will equal 1. Remember, tangent is y over x. And so what is the only way that two things over each other would equal 1? Well, it's got to be if they're the same thing. So look at your ordered pairs in quadrants 1 and 4 and find where your x and your y are the same exact number. Not one positive, one negative, the same exact number. And so you'll notice that you'll see you have the ordered pair, the square root of 2 over 2, comma square root of 2 over 2. Those are exactly the same, and that occurs at pi over 4. So the inverse tangent of 1 is equal to pi over 4. Let's go ahead and do C on this one. So we're looking for the inverse tangent of 0. So that means tangent of what angle will equal 0? Well, this is 0 over, it doesn't matter what number, right? It could be anything. So I'm just going to put I'm not going to put anything. So remember, though, if we're doing y over x, what is the only way that a fraction can equal 0? It's if it's 0 on top, which means I am going to focus on where my y value then is 0. And so the y value is 0 on the x-axis, which is right there, which some of y'all are thinking is probably 2 pi. But remember, we're only looking from negative pi over 2 to pi over 2. So if you're saying, 2 pi, you're in the right location. Your angle's too big. And so if you just subtract that 2 pi, then you'll end up with the correct angle, which is at 0. All right, B. Same thing. We're doing the inverse tangent, so we're looking for an angle. We know that inverse tangent tangent is y over x. So let me rewrite this. And so I know it's y over x. So I'm going to go ahead and put it over 1. Now, when I look at this and I'm looking for my ordered pair, I'm looking for where x is 1 and y is the negative square root of 3. Well, we don't have one exactly like that, but we have one very close to it. And it has the over 2 here. Well, let's see, would that work? If I put the square root of 3 over 2, and I put the 1 over 2, does that make those 2's cancel? It does, because if you multiply the top and the bottom both by 2's, then their 2's would cancel, and you would end up with the negative square root of 3 over 1. So it's okay that we added the 2's on there because they will end up canceling out. So now we're looking for the angle in which we have 1/2 and the negative square root of 3 over 2. And so when we look on our unit circle, we're going to see that that's at 5 pi over 3. But 5 over 3 is almost 2. It's 1 point something, which is not between our negative pi over 2 and pi over 2. So because it's that quadrant 4 angle, guys, remember, sorry, it paused on me there. So we found that it was 5 pi over 3, which is too big. But remember, like we said earlier, if it's in that quadrant 4, you're going to need to find its coterminal angle. So we're going to subtract 2 pi from it, and we'll find that the angle that we're really looking for is at negative pi over 3. And then once again, D says we're going to take the inverse tangent of 5. 5 is not going to be on my unit circle, so I'm just going to do the inverse tangent of 5 in my calculator, and I got 1.373. All right, and so I'm going to stop here, and we will pick up with part 2 of the video, but I'm got it recorded while I'm in a class, so it'll be a little slower. If you need to speed it up, speed it up. If you need to slow it down, remember you can always use pause.